Hi, and welcome to Codex. Our speaker today is my colleague, Henry Adams, who's an associate professor at Colorado State University. His research interests include applied topology, computational topology and geometry, metric geometry, and combinatorial geometry, and he runs the successful Applied Algebraic Topology Research Network YouTube channel. Today, he will tell us about connections between topology and projective codes. Take it away, Henry.
Thanks so much. So I'd really like to thank the organizers, Joey, John, Emily, and Dustin for inviting me to speak today. And I'll be talking about several different things related to projective codes, Borzo-Gluon theorems, Gromov-Hausdorff distances, Vietoris-Rips complexes. I won't really assume that you know what any of those are. And one of my main goals of this talk is just to give you the flavor of things and to show some idea of how they relate to each other. So this talk is sort of combining, in some sense, two recent papers that appeared on arXiv within a month of each other. That when they appeared, we had no idea they were connected at all, but now we realize they're quite closely connected. So the first paper was by myself and my student Jonathan Bush and Florian Frick, based at Carnegie Mellon. And the title of this paper is really the title of my talk. So the topology of projective codes. So what do packings in real projective space have to do with topology? 1 month apart, there was a paper by Borsuk Ulam, Facundo Mamoli, and Zane Smith, all coming out of Ohio State, although some of them have moved on now, on Gromov-Hausdorff distances between spheres. And I'll explain what that is. And we're sort of we're forming a polymath project. So a large collection of faculty and postdocs and students who are either currently at Colorado State, Ohio State, Carnegie Mellon, or Berlin, or formerly at those places, have started talking over the last couple of months, connecting these topics together. And we're learning that by talking to each other, we can figure out the math that we need much more quickly than by working alone. So it's sort of a messy, large, rapidly changing polymath project in some sense right now. So the way I want to organize my talk is the first, say, 25 minutes, I'll be introducing a lot of new things and giving you the flavors of why I care. And maybe on the half hour, I'll try to stop wherever I am and really connect things more directly to projective codes, namely packings in projective space, which this community are the experts on, and I'm definitely not. So I'm hoping you'll bear with me for the first part. Think of this as sort of an introduction to a lot of different related things that do relate to things that I hope many of you know about, but let me meander my way there. All right, any questions before I begin? So my main application will be Gromov-Hausdorff distances. The basic idea is you have two metric spaces, maybe this curve and this finite set of points, and you want to say how close are these metric spaces, okay? So there's many different notions of closeness of metric spaces. Such distances are used in alignment problems. So computer vision, how do you align my tooth to go into the right spots, in my mouth when I'm building a dentistry mold? Gromov-Hausdorff distance is a quite theoretical distance, and it's notoriously hard to compute both in applications or in practice, but a lot of computable distances are based on the Gromov-Hausdorff distance or approximations thereof. And there's several different definitions of the Gromov-Hausdorff distance. I'll just give you one definition that might not be the one you've seen before. So X and Y are compact metric spaces. Twice the Gromov-Hausdorff distance between them is the infimum over all maps I can find going in each direction. So I need a map from X to Y and a map going backwards. Okay, so I can search for the best possible pair of maps I want. Okay, but once I have those maps, each map has something called a distortion, and the two maps together have a co-distortion. And the largest of the distortion or the co-distortion is this Gromov-Hausdorff distance. Okay, so in my picture, maybe X is the two sphere, Y is the circle. I'm looking for the best possible maps. These maps do not need to be continuous, which for a topologist is frustrating and a challenge because when we have good, as topologists, we have good obstacles for obstructions for describing when continuous maps can exist, but not necessarily discontinuous maps. All right, so let's look at one map G. What's its distortion? Well, you find the worst 2 points in the domain, X and X prime, where worst is how much have you distorted distances between X and X prime. This is a distance taken in X, and their images in Y. So this is a distance taken in Y, right? So how much have you distorted distances as you map from X to Y? You know, look at the worst distortion. That's the distortion of the map. So the distortion of H going backwards is the same. I need to tell you what co-distortion is. In this talk, actually, we won't use co-distortion because we're going to put bounds on the Gromov-Hausdorff distance. Only by bounding the distortion, it'll turn out. But what is the co-distortion? It's sort of a mixing. You now involve both maps. So look at the worst pairs of points where little x is in space X, little y is in space Y. You map little x into Y using your map G. You map little y to X using your map going backwards, H. And then you just compare these distances in X, how far apart are they compared to these distances in Y, okay? And the furthest apart those distances can be over all pairs of points, little x and little y, that's your co-distortion. Questions? Not too hard to define, but if you ask like, what's the Gromov-Hausdorff distance between, I don't know, like a unit square and a circle? I mean, nobody knows. You can get good bounds, but knowing these distances exactly is really difficult. These distances are used all the time in differential geometry. Gromov was proving important theorems using these distances. All right, and as I said, we'll put bounds on these distances, but always just bounding the distortion is the only term we'll need to bound. Lim, Mamoli, and Smith, in a recent paper, they consider the question, what are the Gromov-Hausdorff distances between spheres of different dimensions, okay? And I'll always talk about twice the Gromov-Hausdorff distance. So the spheres are going to be equipped with a geodesic metric, a path length metric, and they have diameter pi, because the furthest apart you can get in a sphere is just from the North Pole to the South Pole, and that is pi apart. They find 3 Gromov-Hausdorff distances exactly: the distance between the circle and the 2-sphere, the circle and the 3-sphere, and the distance between the 2-sphere and the 3-sphere. Okay. So the distance between the circle and the 2-sphere is 2 pi over 3, which is the diameter of this inscribed equilateral triangle in the 2-sphere, right? These 2 points are distance 2 pi over 3 apart. And then the distance between the 2-sphere and the 3-sphere is R2. R2 is the diameter of the inscribed tetrahedron in the 2-sphere, okay? So inscribe a tetrahedron in the 2-sphere, and R2 is this length. More generally, inscribe an n+1 simplex in the n-sphere, and its diameter is Rn. They prove these lower bounds. So, the distance between the n-sphere and the n+1 sphere is at least Rn. People would conjecture that the distance is actually equal to Rn, these diameters of inscribed simplices, but we don't know that. So this is our distance matrix of Gromov-Hausdorff distances between spheres. It's a distance matrix, so it's symmetric. And all of the non-zero entries are between pi over 2 and pi. And you know, as you start going down, these values are sort of approaching, you know, pi over 2. As you move this direction, the entries are probably approaching pi. I think that's known. Those entries are approaching pi. Yeah. So think of pi as a large distance and pi over 2 as a small distance here. They get lower bounds on all entries in this table in terms of covering numbers of the sphere, but these bounds are not tight. Let me describe these covering numbers. So X is a metric space. The kth covering number is going to be the smallest R that you can find, such that if you draw K balls in your space, each of radius R over 2, then those balls cover your space. Okay. A whole bunch is not known about this table. I mean, people would predict that these distances are monotonically increasing as you move across a row. That's not even known. Yeah, any questions here?
I guess there's a optimal map from S1 to S2 and S2 to S3. Is there a way to describe that map?
Yeah, so I'll describe the optimal map between S1 and S2. The other ones are quite complicated, okay? So the map from S1 to S2 is just the inclusion map onto the equator. The map from S2 back down to S1, you divide the northern hemisphere into 3 sort of triangular shaped regions, okay? And then you map each triangular shaped region down to a single point in the circle, okay? So on the northern hemisphere of the 2-sphere, I have 3 triangular shaped regions that just map to 3 equally spaced points on the circle. Okay. And then on the southern hemisphere, I do the same thing, but I rotate things 1/6 of the way around. So it's very much a discontinuous map from the 2-sphere down to the circle.
That's pretty wild. I would have guessed that you just slide down to the equator along a longitude line. Yeah.
Right, and the problem with that, let's see, we could probably figure this out, is that points near the North Pole are going to go to distance pi apart. Yeah.
Awesome, thank you.
So I should say they find maps that give these distances exactly, right? Their maps don't easily generalize to these other entries, but you know the hope would be to find other maps that also give these values that generalize to give other values here. Okay, so how I got involved was sort of some recent improvements, and there's some notation here that's not defined, but I'll define soon. We're able to provide more general lower bounds for all entries in the table. These lower bounds are tight in all known cases, but it's of course not known to be tight everywhere. Let me just say that our lower bound gives lower bounds in terms of coverings of the projective space that are actually better, okay? So we're trying to produce these lower bounds. And so we want the value on the right-hand side to be as large as possible, okay? So that means we want these covering numbers to be as small as possible, okay? Our coverings are in the projective space. So in some sense, you only need to cover half of the volume that you needed to cover in the sphere, right? So you can get away with smaller balls covering projective space than you needed to cover the entire sphere. So that's sort of the packing or covering explanation for why our bounds are an improvement. Yeah, but this inequality is not likely tight, but this one potentially is tight in many cases. So my next challenge is going to be introducing the things you need to know to understand this definition here, but let me give you an intuitive explanation, okay? A Rips complex of an n-sphere is a way to thicken it, okay? So we're trying to thicken the n-sphere in some sense. Think of the n-sphere as the smaller dimensional sphere and the k-sphere as the larger dimensional sphere. So what this bound here is equal to is how much do we need to thicken the n-sphere until we sort of obtain the topology of the k-sphere, or in other words, we admit a nice map from the higher dimensional sphere. Okay. So how much do we need to thicken the lower dimensional n-sphere until we admit a nice map from the higher dimensional k-sphere? And I'll spend some time defining these things precisely, but we're going to call this value CNK. CNK is the scale R such that I need to thicken the n-sphere by a scale R to, in some sense, obtain the topology of the higher dimensional k-sphere. Questions so far? All right. What's fantastic about the Lim, Mamoli, paper is they relate these Gromov-Hausdorff distances to the Borzo-Gluon theorem, which is a classical result in topology about continuous maps. And this is for their lower bounds. So to give lower bounds, you sort of use topology, the Borzo-Gluon theorem. To give upper bounds, you need to find explicit maps that minimize this distortion and co-distortion. So a Z2 space is just a space equipped with a free involution. You can sort of swap each point with its antipode. Spheres have this free involution that map each point to its antipode. And we're going to build thickenings on the spheres, and the thickenings of the spheres are also going to have this antipodal map. Okay. And an odd map between two such spaces is just one that respects that antipodal action. So if you start at X, take its antipode, and then map over via your map, that has to be the same as first mapping over and then taking the antipode. All right, so an odd map respects this antipodal map on your space. And one version of the Borso-Ulam theorem is that if you have an odd map from a higher dimensional sphere to a lower dimensional one, then it has to be discontinuous. Okay. Vietoris-Rips complexes are a popular tool in computational topology, which is my area of background. And they're a way to thicken a metric space. So start with a metric space, maybe this subset of roughly 10 points here, and then choose a scale R. You build a simplicial complex by throwing in all simplices whose diameter is at most R. So maybe R in this picture is 1 inch, and whenever two vertices are at most 1 inch apart, I throw in an edge between them. And then if I have all 3 edges forming a triangle, I automatically glue in the triangle. And if I have all 6 edges forming a tetrahedron, I automatically glue in the tetrahedron. The reason why Vietoris-Rips complexes will be valuable for us is because you can take a discontinuous map, such as a map that's related to Gromov-Hausdorff distances, and induce a continuous map on Rips complexes. Okay. However, you're going to have to increase the scale parameter when I map over from X to Y. How much do I need to increase the scale parameter? Well, by the distortion of the map. Okay. And the idea here is, let's say I have an edge in X, 2 vertices in X that are, let's say I have an edge in the Vietoris-Rips complex of X. So I have 2 vertices in X that are at distance R apart. Okay. I want to map that over into Y, but it better hit an edge in the Rips complex on Y. Right? How much could the distance increase when I map over to Y? Well, it could increase by the distortion of this map. All right. And so if the 2 points in X were distance at most R apart, and Y, they could be at most distance R plus the distortion of this map apart. And that's sort of the relationship to this whole Gromov-Hausdorff business. Gromov-Hausdorff distances care about discontinuous maps, but to produce topological obstructions, we need to sort of transform these possibly discontinuous maps now into continuous maps between thickened spaces. Questions so far? All right, so my prior work has sort of looked at Rips complexes of spaces, such as circles and spheres. And I won't explain the intuition here, but as you thicken the circle, eventually you reach this scale parameter, 2π/3, where this triangle appears. And at that scale, the topology of the Rips complex changes to a 3-sphere, okay? And then you thicken more, and you reach the scale 2π/5, and the topology changes now to the 5-sphere, okay? And if you'll remember, these lower bounds, C and K, were sort of how much did we have to thicken the lower dimensional N sphere until we admitted an odd map from the K sphere, right? So let's think of N equals 1. How much do we need to thicken the circle until we admit an odd map, say from the 3-sphere, okay? You don't have an odd map from the 3-sphere into the circle, but if you thicken the circle by 2π/3, you get the 3-sphere, right? And then you do admit an odd map from the 3-sphere into the 3-sphere. So these values are sort of how much do you need to thicken the circle to admit an odd map from the 3-sphere or the 5-sphere. And they appear in this table as our improved lower bounds. I won't talk as much about the N sphere, but just to say that the first scale at which the topology of the N sphere changes is when you glue in these inscribed N+1 simplices into the Rips complex, okay? So these scales at which the N sphere changes topology correspond to these super diagonal entries in this Gromov-Hausdorff table. And this sort of pattern matching is sort of what led us to make conjectures that led to proofs of these lower bounds. All right, that was quite quick, but questions about Rips complexes?
This is related to some of the stuff that Michael Moy worked on, correct?
That's
I'm
right.
just trying
yeah.
to like think about in my head. So with these continuous sort of Vietoris-Rips complexes, so it's like with the circle, when the diameter is really small, then you're sort of just like making little lines and segments, and then it's just like once you get big enough, then it kind of starts popping over to get the triangles. Is that how you should think? Or
That's right. So we're building some simplicial complex on top of the circle. So here's the original circle, and then at small scales, I add in all these short edges. Okay, but I also add in small triangles and small tetrahedra, right? But eventually the scale increases until I hit 2π/3. And at that point, I add in these equilateral triangles, okay? If you just glued in one equilateral triangle, you'd sort of fill in the circle and get something contractible. But we actually glue in a circle's worth of equilateral triangles, and that gives us a 3-sphere, turns out.
okay, yeah, thank you.
So if I have a map F from X to Y, how do I define its extension to the complex, the VR complex?
Yeah, thanks. I should have said that, so we're defining a map between simplicial complexes. So we only need to define where the vertices go, and then simplices are where simplices get mapped or defined by their vertices. So just the vertices are just the points in your metric space. So map X to f of X.
So you extend convexly or something?
That's right. So, if my vertices of the edge go here, then that edge just goes to the simplex defined by those same vertices.
Are these convex combinations formal? Or do I think of Y as being in a Euclidean space?
No, think of these convex combinations as formal, essentially the barycentric coordinates on a simplex.
Great, thank you.
Yeah, I mean, so this is just a simplicial map, right? So to define a map between simplicial complexes, you just define a map on the vertices, but you need to check that every simplex in the domain maps to a simplex in the codomain, right? You can't have a filled-in triangle mapping to a hollow triangle. And that's why we need to bump up the scale. Other questions? Okay, so what comes next, I'm just going to give some high-level ideas regarding proofs, but not go through the proofs, but I just want to give the main points. How did Mamoli Mamoli and Smith prove that the Gromov-Hausdorff distance between the n sphere and the n+1 sphere is at least Rn, the diameter of these inscribed simplices? They used a not very well-known generalization of Borsuk-Ulam. Okay, it's by Dubrinj and Schwartz back in 1981, and this paper has only been cited 6 times or something. Okay, so Dubrinj and Schwartz answered the question: pretend I have an odd map from the n+1 sphere down to the n sphere. Borsuk-Ulam says it can't be continuous; it has to be discontinuous. Okay, and in some sense, they answered, how discontinuous must it be? They proved that this map has distortion that's at least the diameter of the simplex. Okay. We're able to get improved bounds by generalizing this result, not for maps from the n+1 sphere to the n sphere, but from maps from the k sphere to the n sphere for any k larger than n. And the rough idea is that we take a discontinuous map, okay, turn it into a continuous map between Rips complexes, okay, and then we use this continuous map between Rips complexes to map in a k-sphere continuously. And then when we have an odd continuous map from the k-sphere in here, right, CNK was just, the smallest parameter, smallest scale parameter, so that I admitted a continuous odd map from this k-sphere, okay? So once I admit a continuous odd map from this k-sphere, then my scale must be at least CNK by definition of CNK, right? So we're sort of able to bound the distortion by CNK. Let me tie it all together, and then I'll go back for questions. So now we can bound the Gromov-Hausdorff distances between spheres of arbitrary dimension, okay? So I want to bound a lower bound on the Gromov-Hausdorff distance between n sphere and the k sphere. I'll think of the n sphere as the lower dimensional one, the k sphere as the higher dimensional one. So as I explained at the very beginning, this Gromov-Hausdorff distance is determined by maps in each direction and their distortion and their co-distortion. But we're only going to bound the distortion going from the high dimensional sphere to the low dimensional one, okay? This is the only part that we need, okay? So consider a map from the high dimensional sphere to a low dimensional sphere. We're going to bound that distortion. That's what we did in the prior slide, but we only did it for odd maps. But Mamoli and Smith show that if you have any map from a high dimensional sphere to a low dimensional sphere, you can sort of just consider that map on the northern hemisphere of the high dimensional sphere, reflect it through the origin to make it antipodal, and you don't increase the distortion. Okay. So now we have an odd map from a high dimensional sphere to a low dimensional sphere. As in the last slide, you know, we have bounds on that distortion. Okay, so I roughly accomplished my goal. I think I took 30 minutes to explain all this stuff that's relatively new to all of you, giving the flavor and not all the details. So next I'm going to move on to the relationship to projective codes. But let me pause here for questions. Any questions? Okay. So in the prior slide, I outlined this proof. And now I just want to say a couple words about this. Okay. So I've sort of spent the majority of the last 5 years of my career studying the topology of Rips complexes of circles and spheres and other spaces. Okay. And we're learning that they're quite closely connected to coverings and packings in projective space. Okay. So I haven't talked about packings yet, and let me talk about that now. Packings in projective space, as far as I understand, are also referred to as projective codes. Okay. That's something that folks of codex like to study. So here, X is any metric space. I'm going to define the covering number, the kth covering number, as the smallest scale parameter R, such that I can cover my space X by balls of radius R/2. So here's a picture of a covering of real projective space by a certain number of balls. Packings is going to be the largest, the kth packing number is going to be the largest scale, such that I can pack disjoint balls of radius R/2 inside my space. Okay, so here's a picture of a nice packing in real projective space. And you know, these numbers are sort of bounded by each other, right? The covering number is always larger than the packing number because you need larger balls to cover your space, right? And you need smaller balls to pack them in. So in this paper, we sort of relate coverings and packings to the topology of Rips complexes, these thickenings of the n sphere. Okay, so pi is the diameter of the n sphere. And if you can find a covering, you know, a nice covering of your projective space by k balls, right? And nice would be, we want, you know, small radii balls, as small as possible. Okay. Then you're sort of you're sort of saying I can find a scale that's strictly smaller than the diameter of the sphere. I can find a scale strictly smaller than the diameter of the sphere, right? So that I admit a map, you know, an odd map from a high dimensional K sphere into this thickening of the low dimensional N sphere. And okay, give me a moment because I said that wrong. This is a non-existence result. Okay, there's not an odd map. All right, let me try again. Right. Okay. Goodness. Let me start with the moral. The moral is packings, coverings of RPN, this projective space, bound the topology of the Rips complex. All right. So if I have a nice packing, so the packing number is going to be smaller than the covering number, okay? If I have a nice packing, then I can get a scale, you know, bounded away from pi, such that I admit an odd map, okay? But if I make that scale too much smaller, then I no longer admit an odd map. Okay. So if I subtract a little from pi, then I can admit an odd map into the Rips complex. But if I subtract too much, the covering number, then I can no longer admit an odd map. Okay. So this deviation between packings and coverings, I mean, the tighter you can get that, the more precise you can say, how much do I need to thicken my n sphere until I admit an odd map from the K sphere. And as we've seen earlier in the talk, these questions are closely related to Gromov-Hausdorff distances. So in my last, say, 5 to 10 minutes, let me just outline a sketch of this one. So what do projective codes or packings in projective space, what do they have to do with producing odd maps from K spheres into thickenings of lower dimensional spheres? Okay. So here's my proof by picture for this second theorem. Pretend I have a packing of 1 or 2 or 3 or 4 balls in real projective space. I don't claim that this is an optimal packing, but an optimal packing would work. Okay. I'm going to produce maps from maybe higher dimensional odd spheres into the Rips complex of this 2 sphere is what we're going to have. So given this packing in projective space, produce an antipodal packing now in the sphere. Okay, so my pictures are now in the n sphere, where n is equal to 2. I have these antipodal, these symmetric packings in the n sphere. I'm going to use these packings to produce odd maps from K spheres of all dimension n. All right, so in black, I have the 2 sphere. So n is equal to 2. And then here down below, I'm looking at maps from the K sphere in where K is 0, K is 1, K is 2, and K is 3. Okay, it's not hard to get maps from the 0, 1, or 2 sphere into the 2 sphere. But it is hard to get an odd map from the 3 sphere into the 2 sphere. First, I need to thicken the 2 sphere. Some amount. But how do I use these packings to get these odd maps? Well, I'm going to use these packings to produce maps from boundaries of cross polytopes in. Okay, so maybe you've heard of cross polytopes, but they're particular polytopes in Euclidean space. They're the convex hull of the standard basis vectors along with their negatives in Euclidean space. Okay, so in the real line, if I take E1 and negative E1, those standard basis vectors, their convex hull is an interval, and the cross polytope, the boundary is just these 2 points, which is a 0 sphere. Now in 2D, if I take the standard basis vectors and their negatives, I get a diamond, and its boundary is a circle. In 3D, if I take the standard basis vectors and their negatives, I get this solid 3-dimensional ball whose boundary is an octahedron, a 2 sphere. And in 4D, okay, I have this convex polytope. It's a 4-dimensional ball. Its boundary is a 3 sphere. All right. The relationship with packings comes as follows. The distance between antipodal points is pi, right? So I don't want to thicken my space by pi. I want to thicken my space by less than pi and still have nice maps from these K spheres in. But the condition on this packing is sort of saying these 2 points on the same hemisphere, their balls are disjoint, which means if I reflect one, then these 2 points are sufficiently close together so that there exists an edge in this Rips complex at not too large of a scale. Okay. So again, these balls being disjoint in the packing means that if I reflect one, these points are sufficiently close so that the edge is present in the Rips complex. Okay. So in these cross polytopes, I don't have these antipodal edges, but I do have all the other edges, right? But my Rips complex has thickened things enough so that these edges are present in the Rips complex So I can map in, this 2-sphere here, which is a cross polytope, or a 3-sphere here I can map in, which is a cross polytope. Questions on that argument?
So are we constructing a continuous odd map from SK to the Rips complex?
That's right. And this is just a picture of it. And the point is that you use this bound to prove that all of these edges are in the Rips complex. And these edges are in the Rips complex, so are their faces, right? So, these 3 edges being in the Rips complex means that this triangle is in the Rips complex.
So I project the sphere to the cross polytope in the same space, and then I pass it to here through this continuous map. I see.
That's right. Yep. You're sort of mapping the sphere first to the boundary of the cross polytope. And then I'm showing this map from the, I sort of think of the boundary of the cross polytope as the same thing as the sphere, but you're exactly right. Yeah. So let me end there and just go to questions. I know very little about packings or coverings. Many of you are experts, I think more in packings, because those are projective codes. But yeah, many of you are experts about packings, not only in projective space, but also Grassmannian's complex projective space. So I'm interested in the more results, the better about packings in these various spaces, because we can sort of take such results about packings and turn them into results about topology of Rips complexes. So references that I know of about packings, I know of references by Brook and Cox, Trop, Frickus, Jasper, and Nixon. I know of this Game of Sloan's, I think, webpage by, I believe, King and others. And I know of a table by, I believe, Nixon and Frickus. But yeah, I mean, in our archive paper, this is one result about packings that we translate into a result about Rips complexes. I won't dwell on what either result is, but I think there's a correspondence here that's worth exploring. And maybe the better explanation here is we know a lot about the topology of Rips complexes of the circle. We know very little about the Rips complexes of the n-spheres. Essentially, everything beyond this first change in scale is unknown. So there's a huge question mark here, okay? But packings and coverings, I feel, are really gonna dictate what we can say here. Maybe we can't give precise results, but we can say things in terms of packings and coverings along the lines of these statements, right? If a scale is small or large compared to a packings or coverings of projective space, then we can say things about the topology of these spaces. And I'll end with some other questions. I mainly spoke about lower bounds for Gromov-Hausdorff distances. It'd be nice to try to find accompanying upper bounds by building maps of low distortion and co-distortion. Fukuna Mamoli, Sunyuk Lim, Zane Smith are thinking about this. Amzi Jeffs has some nice, very recent new results along these lines, I think. We sort of used equivariant topology here. Can you use it to bound Gromov-Hausdorff distances between other spaces, maybe with G equivariant actions instead of Z2 equivariant actions? And I think I'll leave it there. So thanks very much for your time and attention and questions.
All right, thank you very much for that excellent talk.